These are some review problems for an exam in a Calc 2 course. Main focus here is techniques of integration here, just various integration by parts and partial fractions and substitutions and trig integrals and this kind of thing. All right, first question here. We want to evaluate the integral of natural log x over x dx. So with all of these, I think the first thing I try and do is find a substitution, see if that works out, and that's actually going to sort of be fine here. So there may be more complicated things you do, but a quick u-substitution will work. And the trick here is I'm going to have my integral. I have natural log x over x. I'm going to think of that as natural log x multiplied by 1 over x dx here. So I'm going to rewrite my integral that way. Then what I can do is I can let u equal natural log of x, and then du is 1 over x dx. Well, then what I have du 1 over x dx, I've got my 1 over x dx sitting right here. And so the substitution using u, so I get an integral, natural log x is u, 1 over x dx, that's du. So our substitution worked pretty simply here. Now I just need to integrate. I get u squared over 2 plus c, and then I need to convert my u's back to x's. U is natural log x. So what I end up with is natural log x squared over 2 plus c. So fairly straightforward here, although the tricky part is knowing what technique to use and then applying it. Okay, second question in our review, we want to do an antiderivative of 2x minus 3 times e to the x squared minus 3x plus 1 dx. Again, you start thinking, well, there's multiplication. Maybe I could do integration by parts here. But before that, I'm going to start looking for a substitution. And generally, when I've got e to some power, particularly if that power is somewhat complicated, a substitution to try is to let u be the exponent. So what I'm going to do is I'm going to let u be, not e, but x squared minus 3x plus 1. So I let u be the exponent for e. And then du would be, let's see, 2x minus 3 dx. Well, that was convenient. Note this 2x minus 3, that's also in our integral. So essentially, I can rewrite my integral here. The e to the x squared minus 3x plus 1, that's e to the u. And then I can combine the 2x minus 3 and the dx as a du. So you then evaluate that. Antiderivative e to the u is just e to the u plus c. And then you got to put your x's back. And so you end up with e to the x squared minus 3x plus 1 plus c. So again, a pretty straightforward u-substitution problem. Tricky part is identifying that that's what you should do. Next question. Here we have an initial value problem. dy over dx equals y plus 1 times x minus 1. And our sort of y when x is 0 is 4. So y of 0 is 4. We're thinking of y as a function of x. Okay, so now one technique, probably the only technique we've done in our course here, is dealing with separable differential equations. This happens to be separable. So what I'm going to do is put everything with a y on one side, everything with an x on the other. So I'm going to get dy. I can divide the y plus 1 to the left, and then the dx is going to go to the right here, and I'm left with an x minus 1 dx. So I'm just sort of separating this, taking the dy dx there, writing it, sort of treating those as like a fraction essentially here. And then what I can do is I can integrate both sides. So I get 1 over y plus 1 dy equals an integral of x minus 1 dx. And then we're going to integrate both sides. So antiderivative y plus 1, I could do a u equals y plus 1. This is natural log absolute value y plus 1. Antiderivative of x minus 1 is x squared over 2 minus x. And then I need a plus c, can be on the left or right, doesn't matter. I guess you could do both, but then if you subtracted them, you just get one constant here. So there's our sort of equation so far. And now I'm going to use this y of 0 equals 4. So y is 4, x is 0. I'm going to use that to solve for c. Before I do that, though, I'm going to kind of rewrite this to look a little bit nicer here. So I want to essentially solve for y, typically is what I'd prefer to have. Sometimes you can't do that. But here I can go e to both sides. So I can go e to the natural log absolute value y plus 1 equals e to the x squared over 2 minus x plus c. And then what I get, e to the natural log y plus 1, Well, that's just y plus 1. Now, technically, I should have absolute values here. And then on the right, I'm going to do something that feels a little bit weird here maybe at first. Do e to the x squared over 2 minus x. And then because I'm just adding something, there's a rule of exponents that says I can write this as times e to the c. Now, I could write this as e to the x squared over 2 times e to the negative x times e to the c. But what I'm trying to do is sort of pull the constant out, that c, on its own. So I kind of want to keep the x's together. Okay, so now I get y plus 1 absolute value equals, now this is a weird thing in a differential equations land, but typically we see this e to the c here, and we really think of that c as c1. So I'm going to put some subscripts here, c sub 1, just go back, put those c sub 1s, and then I'm going to think of really c as e to the c1 here. This is a customary thing that happens in differential equations, although without the stuff in red here. So often people would take this and just write it as c times e to the x squared divided by 2 minus x, with the understanding that the c here is different from the c here. In fact, the c here is e to that c here. Still just a constant that we've been solved for, so it doesn't really matter a whole lot. You might be worried here that e to the c is always positive here, so maybe what we've got here, maybe you solve for a negative c, but we've got an absolute value over here, so that'll always be positive anyway. All right, now I'm going to plug in x is 0, y is 4 from my initial condition. So I'm going to get absolute value 4 plus 1 equals c times e to the 0 squared over 2 minus 0 here. So that gives me 5 equals c times e to the 0, which is 1, tells me my c is 5. So I use my initial condition to solve for that constant. And then what I have is I can go back up to sort of my general form here. My absolute value y plus 1 equals c times e to the x squared over 2 minus x, and plug in for c. So I get is absolute value y plus 1 equals c is 5. I get 5 times e to the x squared over 2 minus x. Now, we don't have a plus c here because that sort of got turned into a multiply when we solve for y by taking an exponential. Now we want to think about this absolute values here. So I kind of want to get rid of the absolute values. So y plus 1, well, I know from my initial condition, whoops, sorry, jumping around here. I know from my initial condition, y of 0 is 4. So when x is 0, y is positive, we're generally going to think about y as staying positive all the time, or else we get some sort of continuity or maybe some differentiability issues. So really, I'm going to assume that means y will always be positive here. So essentially, I'm going to get y plus 1 equals 5 times e to the x squared over 2 minus x. And then I can subtract the 1. So I get y equals 5 e to the x squared over 2 minus x minus 1. So there's our solution to our differential equation. Next question. We're going to do an antiderivative of e to the x times a hyperbolic cosine of x dx. Okay, this one, I see two ways to do this. One of them is probably going to be a lot friendlier than the other. So probably as I tend to do this, let's do the way that's maybe not quite as friendly here. I'm going to do this doing integration by parts. It'll work out just fine. I'll just take some work. So I see this as a multiplication of e to the x and hyperbolic cosine of x here. I'll just remind you the hyperbolic cosine and hyperbolic sine, their derivatives and integrals work like cosine and sine, except there's no negatives that show up. So the derivative of a hyperbolic cosine is a positive hyperbolic sine. Derivative of hyperbolic sine is a positive hyperbolic cosine. So here, what I can do is I can do integration by parts. I can let u be e to the x. I can write dv to be hyperbolic cosine of x dx. And then du, I differentiate e to the x. I get e to the x dx. V, I integrate my hyperbolic cosine. That's just a hyperbolic sine. So integration by parts formula then is u times v. That's e to the x times hyperbolic sine of x minus the integral of v du. So that's going to be, I'm going to write it this way, e to the x times hyperbolic sine of x dx. So we did that here. Now, what we need to do is do e to the x times hyperbolic sine of x integral. So to do that, let me switch to, let's keep doing this. I'm going to do integration by parts again here. So what I'm going to do now, when I do integration by parts again, box that one up over there, my second integration by parts, so let's just go here. How about antiderivative e to the x hyperbolic sine x dx? I'm going to let u be e to the x, and I'm going to let dv be hyperbolic sine of x dx. Then du is e to the x, v is hyperbolic cosine. Note, same thing as over here, I just replaced cosine and sine. Let's switch those around. So this integral of e to the x hyperbolic sine of x dx, well, what's that? U times v is e to the x times hyperbolic cosine of x minus integral v du, which is e to the x times hyperbolic cosine of x dx. Okay, so now I'm going to take this and put that where I have e to the x sine x, antiderivative of e to the x sine x, in my original equation. So let's go down here, work that out. Let's see, so I'm going to get antiderivative e to the x hyperbolic sine x. Let's maybe write up what we're doing. Antiderivative e to the x cos x dx equals this part minus this stuff in the red here. So that's e to the x cos x minus an integral e to the x cos x dx. That's sort of what we've gotten to. Now, the general idea here is we still have this integral to do, but it's what we started with. So we can go and maybe work some stuff out here as we go. Except I think I made a mistake because I see another antiderivative there. Not what I want. So this was e to the x sine x. That shouldn't have an antiderivative. So, whoops, sorry. Navigational issues here. So this e to the x sine x, I want to get rid of that antiderivative. Okay. So what we get now, if you look at this, let's distribute things. You get an integral e to the x cos x dx, antiderivative, should be e to the x sinh x, distribute the negative, e to the x cos x here, and then minus a negative is plus integral e to the x cos x dx. Okay, now the standard thing that you hope happens here is that you can somehow solve this as an algebraic equation for this integral e to the x cos x. You've got two of those, but a kind of curious thing happens here. If you subtract these from both sides, these integrals, they're going to cancel out. And what you're left with is this sort of weird equation, e to the x sinh x, so you get a 0 on the left, equals e to the x sinh x minus e to the x cos x. Here. Now, this seems a bit weird. I should be able to solve for x, but I'm getting essentially cos x equals sinh x here. So that tells me probably actually that something went wrong. Okay, so recap here of where we were. We had done e to the x times cos x dx, the antiderivative here, and we'd done integration by parts. We had to do this twice, and we got down to this somewhat confusing equation here of, well, it says 0 equals e to the x sinh x minus e to the x cos x. Now, there's one little thing that I didn't really account for, is this antiderivative really should give a constant. So I'm just going to put that in here, equals this whole antiderivative should have a plus c here. It's not really 0, it could be a constant here. And the weird thing here is e to the x sinh x minus e to the x cos x. When you look at this here, turns out that this thing on the right, despite what it looks like, I guess I should have my plus c here, this thing on the right is actually a constant. So let's work that out. E to the x, there's a formula for sinh x involving e's. Hyperbolic sine is e to the x minus e to the negative x over 2. Minus e to the x. Hyperbolic cosine is e to the x plus e to the negative x over 2. plus c. So you get 0 equals, and then here we can distribute the e to the x's. So we get e to the 2x minus e to the x times e to the negative x is actually 1 over 2, minus e to the x times e to the x is e to the 2x. E to the x times e to the negative x gives us a plus 1 over 2 plus c. And then what you've got is e to the 2x over 2 minus e to the 2x over 2. Those cancel. You have a minus 1/2 and then a minus a 1/2. This gives you negative 1 plus c. This equals 0. Well, all this tells you is that constant is actually 1 works out. So the two sides here were not the same. Well, at least if you assume constants were 0, they differed by a constant here. So in essence, really, we did all this work. What we got was essentially nothing for how to do an antiderivative of e to the x times cosh x, which was our original question. So we, whoops. So we'll go here. Guess we got some integration by parts practice. We want to do e to the x cosh x here. dx, and we didn't figure that out because the integration by parts, when you did that twice, the two sides that e to the x cosh x ended up canceling out here. Okay, so what can we do? Well, what we can do, though, is this analysis here, we can use some of these formulas. So we're going to start over here and do really what's probably the way this is intended to be done right away here, and that's if I do an antiderivative e to the x cosh x dx, before taking the antiderivative, use the formula in terms of e to the x's for cosh x. So that works out being that hyperbolic cosine is e to the x plus e to the negative x over 2 dx. So we'll sub that in. Then we can distribute the e to the x's. I can pull the over 2 out as a 1/2. Let's do that. And then e to the x times e to the x is e to the 2x. E to the x times e to the negative x is plus 1. And we got something that we can handle pretty easily for integration. So this is 1/2. Antiderivative e to the 2x is e to the 2x over 2. You could do a u sub where u equals 2 to the x. Antiderivative of 1 is 2. You get a plus c. And this I would probably rewrite as e to the 2x over 4 plus x over 2 plus c. So doing a little bit of algebra, understanding that hyperbolic cosine is really able to be written as exponentials, allows us to do this problem relatively easily. Okay. Next one, we've got an antiderivative x minus 3 times cos x. Now this one, we're going to finally get to use integration by parts in sort of a productive way. Here we have x minus 3 multiplied by cosine x here. And there's no real sort of way around this here. We're going to end up using integration by parts. It's a product, makes us think integration by parts, and there's no other technique that's going to work. So what I'm going to do, I'm going to let u be x minus 3, and let dv be the cosine x dx. Now here, the reason to make that choice as opposed to like cosine x and x minus 3 is that what I'm going to do to u is take its derivative. X minus 3 is going to get simpler when we take a derivative. So du is just dx. And dv, the cosine x dx, we're going to integrate that. Well, when you integrate a cosine or a sine, you get another cosine or sine back, possibly with a negative, but that negative doesn't really make the antiderivatives any worse. So I'm going to do an antiderivative of cosine x, I actually get a positive sine x. So my integral, I do integration by parts, it's u times v. That's x minus 3 times sine x minus the integral of v du. Well, that's just sine x dx. So we get x minus 3 times sine x. The antiderivative of sine x is actually a negative cosine x plus c. Think about derivative of cosine x would be a negative sine x, but we had a positive sine, so we need the negative. But then those two negative signs combine. Gives us x minus 3 sine x plus cosine x plus c. So here's a pretty straightforward integration by parts problem. I guess the x minus 3 might throw people a little bit there, but it essentially works out as if that was x. Next one. Here we're going to do an integral of x squared e to the x. Again, this is a product of two functions that aren't going to combine in some sort of nice way. This is going to be integration by parts again. It's going to turn out to be a little bit worse, however. So what I'm going to do is I'm going to let u be something, either x squared or e to the x. Again, I'm going to think I want to make u the thing that will get simpler when I differentiate. So that's x squared. And then dv will be e to the x dx. I want that to be sort of able to be integrated and generally not get any more complicated or even get simpler. So I get derivative of x squared is 2x dx. Antiderivative of dv, so v, antiderivative of e to the x is just e to the x here. So I kept it actually the same. It didn't get any worse. So what I get, antiderivative of x squared e to the x should be u times v. That's x squared e to the x minus the antiderivative of v du. So I'm going to get a 2x times e to the x with my dx. And now what I'm going to do here, I'm going to pull that 2 out in front, and I'm left with an integral, whoops, not x d to the x, x times e to the x dx. Okay, this, still we're going to have to do integration by parts again, still looks a little bit ugly, but the promising part is we started with x squared, degree 2, and now we have x is degree 1. So that degree went down. If we do this again and the degree goes down by 1 again, we'll end up with e to the x, which we can then integrate. So that's exactly what should happen here. So we're going to do integration by parts again. This time I'm doing integral of x times e to the x. So let's see, I'm going to do u is x, dv is e to the x dx, du is just the derivative of x, that's 1 times dx, v, you integrate e to the x, and you get e to the x. So what I'm going to get here is x squared e to the x minus 2, and then I do my integration by parts formula for the antiderivative of x e to the x in a bracket or parentheses here. So I get u times v, that's x e to the x, minus the antiderivative of v du. That's e to the x dx. So what I get, I have x squared e to the x minus 2 x e to the x. Antiderivative of e to the x is just e to the x. Somewhere I need a plus c because I'm out of my antiderivatives. And now I'm just going to sort of distribute this negative 2 because I think it looks nicer that way. Get x squared e to the x minus 2x e to the x plus 2 e to the x. So minus gives me a positive, plus c. And then some people here would notice I have 3 terms with e to the x. I could factor that e to the x out. So this is e to the x times x squared minus 2x plus 2 plus c. So there's an antiderivative using integration by parts twice. If this was x cubed, you'd have to do integration by parts 3 times and so on. And there's shorthand methods to keep track of the bookkeeping. But this isn't really that bad when you think about it. Okay. Next one, we've got a trig integral. Here it's cosine to the 5th, sine to the 4th. So there's various techniques for antiderivatives for cosines and sines multiplied together to various powers. One of the main ones is that if I have an odd power here, I can pull that one apart and then do a substitution. So I'm really noticing this 5 here is odd. So what I'm going to do is I'm going to rewrite this as cosine to the 4th x times sine to the 4th x times cosine x dx. So what I can do is I get even here in the cosines, and then I get a cosine x here. And what I'm hoping to do here, let me just write it off to the right here, is I want to let u be sine x. And the reason I want 1 cosine x, and the reason I wrote it off to the right there, is then du is cosine x dx. So I already have this sine to the 4th x as u to the 4th. Cosine to the 4th, I want to convert that to sines, and I can do that if it has an even exponent. So what I'm going to do is really, well, what I'm going to manipulate there is I know that cosine squared x plus sine squared x is 1, sort of Pythagorean identity. And so cosine squared x is 1 minus sine squared x. So I can get sort of even powers of cosines by taking this to a sort of higher power here. And I can convert cosine to an even power of x into sines here. So let's do that. First thing, I'm going to think of cosine to the 4th x as cosine squared x squared times sine to the fourth x times cosine x dx. And then cosine squared x is 1 minus sine squared x squared times sine to the fourth x times cos x dx. Okay, now I'm ready to do my substitution. I'm going to do the u equals sine x. So I get 1 minus u squared. Sine squared x is u squared, but then squared. Sine to the fourth x is u to the fourth. Cosine x dx is just du. So now I might not be terribly pleased about having to do this, but at least I got a polynomial out of this. I can see a route to finish. So the way I'm going to deal with this integral is I'm going to expand the 1 minus u squared squared, distribute the u to the fourth, write this sort of more like we're used to seeing polynomials. So first thing, 1 minus u squared is 1 minus 2u squared plus u to the fourth. We have that multiplied by u to the fourth du. And then you distribute the u to the fourth. U to the fourth times 1 gives me u to the fourth. U to the fourth times negative 2u squared is negative 2u to the sixth. U to the fourth times u to the fourth is u to the eighth. And then I do an antiderivative. So I get u to the fifth over 5 minus 2u to the seventh over 7 plus u to the ninth over 9 plus c. So that's almost an answer. But I need to convert my u's back to x's. So let's go back, look at our substitution. U was equal to sine x here. And so what I get is this is sine to the fifth x over 5 minus 2 sine to the seventh x over 7 plus sine to the ninth x over 9 plus c. So kind of complicated looking answer, but there's a process we follow. Next question. Okay, we've got an antiderivative going from, or definite integral, not just an antiderivative, definite integral going from 0 to 2, square root 9 minus x squared. Now this one, when I see this 9 minus x squared, particularly under square root, it makes me think of a trig substitution. And so I'm going to manipulate the equation cosine squared theta plus sine squared theta equals 1. You can rewrite this as cosine squared theta equals 1 minus sine squared theta. So anytime you have constant minus something squared, we can make this something squared be a sine theta, essentially. And then the whole constant minus that thing squared, I can use a trig identity and get it to be a cosine squared. The square root, it'll cancel the square. That'll work out really nicely. So to do that, I have to let x be, now over here I'm saying sine theta, but I need to get that 9. So x squared should give me a 9 sine squared theta. So I want to do 3 sine theta for x, because 3 squared gives me 9. Then dx would be 3 cos theta d theta. So when I do my substitution, I'm going to just leave the bounds here, 0 and 2. I'm going to deal with those later. I'm going to get square root 9. X squared is going to be 9 sine squared theta. And then dx is 3 cos theta d theta. Okay. And so then there's these bounds there in thetas. I could plug in a x is 0, figure out what theta is. X is 2, figure out what theta is. I'm going to deal with that later, though. So what I'm going to get here, just put our question marks here. I can do a square root 9 times 1 minus sine squared theta times 3 cos theta d theta. So this equals integral some bounds. Square root of 9 is 3. Square root of 1 minus sine squared theta is cosine squared theta times 3 cos theta d theta. And 3 times 3, so I get 9 times, now square root of cos squared theta, technically it should be absolute value cosine squared theta, absolute value cos theta. Typically that's not really a concern. Let's see, so if x is 3 sine theta, x goes from 0 to 2, sine theta is going to go between 0 and 2/3. Generally, that's going to be the obvious thing to do, is assume theta is between 0 and pi over 2, and so cosine would be positive. So here, typically if these don't present certain difficulties, you can just kind of let this be cosine or absolute value cosine be just cosine here. So what I get is cos theta times cos theta. That gives me a cosine squared theta d theta. Okay, so another trig integral, when you have just a squared theta, what you do is apply a trig identity. And cosine squared theta is 1 plus cos 2 theta over 2. If you had a sine squared theta, it'd be 1 minus cos 2 theta over 2. And so what we get, let's see, we can pull the 2 out. We get a 9/2. We'll have a antiderivative, about 1 plus cos 2 theta here. And what that's going to give us is a 9/2. Let's see, antiderivative of 1 is theta. Antiderivative cosine 2 theta is going to give us a 1/2 sine 2 theta here. And then, whoops, I want to do a plus c, but I'm evaluating these with certain theta bounds here. So instead of trying to figure out those theta values, I'm going to convert everything to x, and then the 0 and 2, the original bounds, will pop back in. So I could have converted them and then converted them back here, but sort of why bother is really the approach I'm taking. Essentially, I'm doing a indefinite integral and then plugging that into the original integral. Now, before I plug these in, let's think about what we know here in terms of sine of theta values in terms of x. So our substitution was x equals 3 sine theta. So we have, let's just write this here, x equals 3 sine theta. So that means sine theta is x over 3. And if theta is between 0 and pi over 2, you can draw a right triangle. Let me make this bigger. Here, you have theta here, and it's supposed to be opposite over hypotenuse. So that's x over 3. Now this third side, you can use the Pythagorean theorem. Let's call this a here. You should have a squared plus x squared equals 3 squared by Pythagorean theorem. If you solve that, that a will be 9 square root 9 minus x squared. Here. Note, square root 9 minus x squared, that's what we started with originally. That's pretty typical for these problems. If you did that Pythagorean theorem solve and you got square root x squared minus 9, but this was 9 minus x squared, generally that's a sign that there's a mistake somewhere. Okay, so we get this. So we know now sine theta is x over 3. We also know cos theta then, well, that's adjacent over hypotenuse. That's square root 9 minus x squared over 3. You could also find tangent theta would be x over square root 9 minus x squared. Here. So you can get a bunch of these here. But we don't have sine theta, we have sine 2 theta. So there's going to be another trig identity that comes to our rescue. So we're going to get 9/2 theta plus 1/2. There's an identity that says sine 2 theta is 2 sine theta, whoops, cos theta. This is another nice identity to know. And then we've got certain theta bounds here. Now what will happen is the 1/2 and the 2 will cancel. And we have 9/2 times theta, but now we can use sine theta is x over 3. Whoops, well, we should worry about changing to x. I don't really want to put the theta there. So let's find theta in terms of x. Well, if sine theta is x over 3, theta is inverse sine x over 3. Plus, rest of this, sine theta is x over 3. Cos theta is square root 9 minus x squared over 3. And then we're evaluating, these were unknown theta values, or we could have figured them out, but they're really x goes from 0 to 2 because our original bounds where x is going between 0 and 2. So now we just plug these in to evaluate. You get 9/2 when you plug in x equals 2. You get inverse sine of 2/3, which is going to be some kind of ugly value, plus 2/3 times 9 minus 2 squared is 9 minus 4. That's square root 5 over 3. And then when you plug in 0, let's see, inverse sine of 0 over 3 is inverse sine of 0. That's going to be 0. Minus, when you plug in a 0, this x gives us 0, and then we get some other stuff, so that's 0. So in the end, what we get for an answer is 9/2 inverse sine of 2/3. And then if I distribute the 9 halves, the 9 will cancel the 2 3's, the 2 will cancel the 2's, so we get a plus square root 5. So there's our answer. On to the next one. Here. So this one, we're going to do an antiderivative. We're doing x cubed times 1 minus x squared to the 7 halves here. Okay, I've got a couple things that I'm thinking about when I see this. One is, what if I let u equal 1 minus x squared? Can this be worked out somehow? So I can do that. The other thing I'm thinking about is, because this is a 1 minus x squared, if I let x equal sine theta or cosine theta, I can do a trig sub here and hope things work out. So we're going to do two different things. We'll see sort of which one works here. So the first thing, I'm going to let u be 1 minus x squared, and then du is negative 2x dx. Now note, if u is 1 minus x squared, you could solve this, x squared is 1 minus u. And so what I'm going to do is I'm going to rewrite this. X cubed I can write as x squared times 1 minus x squared to the 7 halves times, so the x cubed was x squared, I'm going to put the x over here. So x times x squared gives me the x cubed. And that just essentially gives me my dx. So what I'll get is, I need a negative 2 part of my, or sorry, it gives me my du. I need a negative 2 as part of my du. I'm missing that, so I put a negative 1/2 out in front. X squared is 1 minus u. 1 minus x squared is u to the 7 halves. And then I'm going to get a du with the combination of the negative 1/2 du is going to be the x dx. So this actually worked out pretty well here. What we're going to get now is, because this sort of complicated exponent 7 halves is just on u, we can just distribute that and we get essentially a polynomial, but it has fractional exponents. So I guess technically it's not a polynomial, but it sort of behaves the same way. In any case, we get something we can integrate. So we get is negative 1/2. Antiderivative 1 times u to the 7 halves is u to the 7 halves. Minus u times u to the 7 halves is u to the 7 halves plus 1. That's u to the 9 halves. Then you can integrate both of these. You get negative 1/2. U, let's say I'm going to add 1. U to the 9 halves divided by 9 halves. Minus u, add 1 to 9 halves is 11 halves divided by 11 halves. Here, and then a plus c. And so what I'm going to get is, let's see, is negative 1/2. I'm going to get a 2/9 times u to the 9 halves, but u was 1 minus x squared. Here. Minus, let's see, 11 halves in the bottom gives me a 2/11. This is going to be a 1 minus x squared to the 11 halves. Plus c. And then this 1/2 on the outside, I can cancel the 2's, and I'll bring the negative in as well, just to kind of simplify things. That'll just flip the signs. So I'm going to end up with, if you follow that through, is 1 minus x squared to the 11 halves over 11 minus 1 minus x squared to the 9 halves over 9 plus c. So using this substitution, no trig at all, this worked out fairly well. Okay. Let's use some trig here. So let's copy our integral down. We were doing the antiderivative of x cubed 1 minus x squared to the 7 halves dx. And we should get essentially the same thing we had before. Now the trig idea, let's maybe do this in, how about green here, is I see 1 minus x squared, so I'm going to let x be sine theta. Or you could let x be cos theta. They both work. It's just the dx, if you let x be cos theta, you get a negative, which is something you have to deal with. Not a huge issue, but I think it's a little simpler letting x be sine theta. So dx then is cos theta d theta. And when I sub this in, let's see, what I get is an antiderivative. X is sine cubed theta. 1 minus x squared is 1 minus sine squared theta to the 7 halves. And then the dx is cos theta d theta. So seeing that 1 minus x squared makes me think this is the way to go. And then we get a, let's see, sine cubed theta. 1 minus sine squared is cos squared theta to the 7/2 times cos theta d theta. Let's write that 7/2 a little more nicely. And then here, this is cosine theta to the 2 to the 7/2. You can multiply those. So we get an antiderivative of sine cubed theta times cosine to the 7th theta times cos theta d theta. And then cosine to the 7th theta times cos theta is just cosine to the 8th theta. All right, so now we got a trig integral. We've got multiplication of two trig functions raised to powers, sines and cosines raised to powers. The sine has an odd exponent, so I'm going to split that up into one sine times an even power of sine. So we've still got more work to do here. So I'm going to rewrite this as keep the sine squared theta times cosine to the 8th theta, and then the sine theta is going to go out here. So again, the idea here is that this sine squared theta and that sine theta combine to be the sine cubed theta, but I'm going to do a substitution where, like, u equals cos theta here, and that gives me this essentially as my du. Or maybe x equals cos theta. Okay, before I do that, though, I need to convert this sine squared theta into cosines. And so that's 1 minus cos squared theta times cosine to the 8th theta times sine theta d theta. Okay, now my substitution. Let's see, well, I had x equals sine theta, so let's actually use u. I don't want to use x because that stands for something already. So I'm going to let u equal cos theta here, and then du equals negative sine theta d theta. So we do this substitution. In the antiderivative, let's see, 1 minus cos squared theta, that's 1 minus u squared. Cosine to the 8th theta, that's u to the 8th. Sine theta d theta, that's almost du, but I need a negative. So I'll pop a negative out in front and get a du. And then this is a negative. Let's see, 1 times u to the 8th is u to the 8th. U squared times u to the 8th gives me a minus u to the 10th du. And so we get a negative, let's see, u to the 9th over 9 minus u to the 11th over 11 plus c. Okay, and then u is cosine theta. So what we get here is a negative cosine to the 9th theta over 9 minus cosine to the 11th theta over 11 plus c. Well, then what's cosine theta in terms of x here? So if x is sine theta, well, we know that cosine squared theta plus sine squared theta equals 1. So if x is sine theta, let's see, this would be sine squared theta is 1 minus cos squared theta. So x is square root 1 minus cos squared theta. So x is sine theta here. Or we could write that as 1 minus cos squared theta to the 1/2. Except what we've got is cos theta. So I did that the wrong way. I really want cos theta in terms of x. So I found x in terms of cos theta. I want cos theta in terms of x. So let's do this again. Here, so this tells me cos squared theta is 1 minus sine squared theta. So cos theta, note that's 1 minus x squared here. So cos theta is square root 1 minus x squared, assuming certain things are positive, which is the assumption we're going to make. So we can replace cos theta with square root 1 minus x squared. And so this cosine to the 9th theta, that's, well, what square root 1 minus x squared, that's 1 minus x squared to the 1/2 raised to the 9th. That gives me a negative 1 minus x squared to the 9/2 over 9. And then minus cosine theta is 1 minus x squared to the 1/2, but raised to the 11th is 11/2 over 11 plus c. And then I can distribute the negative. And what I get is 1 minus x squared to the 11/2 over 11 minus 1 minus x squared to the 9/2 over 9 plus c. So we get this, and that hopefully matches what we had above. You can see we got the same thing above. So I think this trig route is probably more complicated here as you go along here. But this substitution works as well. Also note, we did 2 substitutions here. And typically when you chain substitutions together, it means you could have done 1. So we did an x equals sine theta, and then a u equals cos theta. And then we did our antiderivative in terms of u's. So we could have just done 1 substitution, gone x straight to u. So let's see what that would have looked like here. So we have x equals sine theta. And then u equals cos theta. Note here that means that, let's see, u squared plus sine squared theta equals 1. So it's cos squared theta plus sine squared theta equals 1. So sine squared theta is 1 minus u squared. So sine theta is square root 1 minus u squared. So x, in theory, we could have done x is square root 1 minus u squared. Note that's x is square root 1 minus u squared. We'll square both sides. That gives you x squared equals 1 minus u squared right away. Or u squared is 1 minus x squared, perhaps to the 1/2 here. So you could have tried that substitution. That's pretty close to what we had up here. Might be something to try to see if that works out. Okay, I'm going to move on to the next one, though. Okay, here we've got an antiderivative. Whoops. Jumped ahead. Antiderivative square root x squared minus 4 over x to the 4th. Now, again, this one, I mean, you can try different things. Sometimes these square roots, you move certain powers ahead, up, and things happen. You can maybe try and pull out an x over x to the 5th and maybe let u equal x squared minus 4 here. Sometimes things like that work out. What I'm going to focus on here is I see x squared minus 4. And that tells me I can do a certain trig substitution and this should work out. So I see u is x squared minus, sorry. I see the x squared minus 4. And what I'm going to take advantage of is I know cosine squared theta plus sine squared theta equals 1. I can get another identity by dividing all 3 of these terms by cosine squared theta. So I just divide by cosine squared theta, divide by cosine squared theta, divide by cosine squared theta. And I get a 1 sine squared theta plus over cosine squared theta, tangent squared theta, equals 1 over cosine squared theta is secant squared theta. And now I want to get the trig function squared minus a constant, so I can subtract the 1, and I get tan squared theta equals secant squared theta minus 1. So except for the 4 versus a 1, we can correct for that. That's essentially what we have. So what I'm going to do is I'm going to let x equal essentially secant theta, but I want to make x squared 4 secant squared theta, so I'm going to put a 2 here because 2 squared would give me 4. And then dx would be 2 derivative of secant theta is secant theta tangent theta. And then I did dx there. Okay, so what I get is an antiderivative square root x squared minus 4 is 4 secant squared theta minus 4 over x to the 4th, that's 2 to the 4th is 16, secant to the 4th theta, and then I get my dx, which is 2 secant theta tangent theta d theta. And I'm going to put that down here because my screen doesn't work so well on the edge. All right, so I'm going to jump this integral down here. Let's see what we've got. We've got 2 over 16 gives us an 1/8 here. Secant to the 4th, we have a secant. I can get just a secant cubed on the bottom. In the square root, I can write that as 4 times secant squared theta minus 1. So we have the secant to the 4th cancel the secant is secant cubed theta. And then we have a tangent theta d theta. So I suppose that tangent theta is really in our numerator here. I can pull the square root 4 out. That's going to be a 2 once you do the square root. So 2/8 will turn into a 4th. Then we have square root of secant squared theta minus 1. That was our tangent squared theta. Over secant cubed theta. I'm going to multiply that. Let's just put this up in the numerator. tangent theta d theta. Okay, so what we end up with is 1/4. This square root tangent squared theta, I'm going to use a tangent theta. I'm going to make the assumption that theta is between 0 and pi over 2, so I don't have to worry about this being absolute value tangent theta. And I get a tangent squared theta over secant cubed theta d theta. So I get tangent theta times tangent theta is tangent squared theta. Okay, now I need to deal with this somehow. You get these integrals with the tangents and the secants here. One trick you can use is to convert everything to sines and cosines and see if something nice happens. So let's try that. So we get 1/4 antiderivative. Tangent squared theta, that's going to be sine squared theta over cos squared theta. And then secant cubed theta would be 1 over cosine cubed, but that's going to go to the top as a cosine cubed. Here. Let's write that a little more nicely. Cosine cubed theta over 1. So this cosine cubed theta over 1, that's really 1 over secant cubed theta. Here. So what I get is 1/4. See, cosine squared, cosine cubed sort of cancel, and you get sine squared theta times cos theta d theta. Okay, now we're in business. I can do another substitution. Let u equal sine theta, and then du is cos theta d theta, and then I have 1/4 sine squared theta, that's u squared, cos theta d theta is du. So I get 1/4 times u cubed over 3 plus c. So I'm essentially, on the way to being done. I just need to convert u's back to x's. So let's see, I'll get a 1/4 times 1/3 gives me a 12th. U cubed, that's sine cubed theta. And then sine theta, I need to convert back to x's. So we had, let's see, our original substitution was x equals 2 secant theta. So let's work on that. X equals 2 secant theta. We need to figure out what sine theta is. So this I'm going to rewrite as x over 2 equals secant theta. Note, this is the same thing as cos theta is 2 over x. And so I can draw a right triangle. Here's theta. Cos theta is adjacent over hypotenuse. That's 2 over x. And then I can use the Pythagorean theorem. I should get 2 squared plus this squared equals x squared. So this is going to be x squared minus 4. So if you squared this, you get x squared minus 4. Plus 4, the minus 4 plus 4 cancel, you get the x squared. Note again, this square root x squared minus 4, that's what we had under the square root originally. And that's, again, typical of these. All right, so what that means is that sine theta should be opposite over hypotenuse. That's square root x squared minus 4 over x. And so what you get here is 1/12 times square root x squared minus 4 over x cubed plus c. I might kind of rewrite this. Let's see. This is x squared minus 4 to the 3 halves over 12x cubed plus c. Perhaps other ways to rewrite that. But we did a trig substitution using the secants and tangents. Really, x equals secant theta, or some multiple secant theta, because we had x squared minus a constant. We got a kind of nasty looking integral in tangents and secants, but a standard trick is convert everything to cosines and sines and just hope something nice works out, and something fairly nice really did. All right, next question. Here we've got an improper integral. We want to determine whether this improper integral converges or diverges. So this particular one, first of all, why is this improper? A lot of our improper integrals, we have bounds that are infinity. This one doesn't. Well, the issue is if you plug in 2, you get 4 minus 2 squared. That's 4 minus 4. That gives you 0 in the denominator. So whatever the graph of this function looks like here is that when I've started at 0, so at 0 I'm actually at 0. And then I'm at 2, I'm going to get presumably a vertical asymptote, and this is going to go up like that. And I'm trying to find the area under here, but again, it's this idea of really a limit here. So it's sort of an infinitely tall area, but presumably it's getting infinitely small up here. It's a question of, does it get infinitely small faster than it gets infinitely tall, or vice versa, in some weird sense of the word faster. So to do this, what I'm going to do is just try and evaluate the integral here. So I have 4 minus x squared on the bottom. I'm thinking, because of the last few problems I did, of a trig sub. That's going to get a little bit ugly. This is actually simpler. I can do a u-substitution. So I can do a u is 4 minus x squared. Then du is negative 2x dx. And so what I'm going to get is an antiderivative. I have x dx. So that would be let's say x dx is negative 1/2 du. 1 over square root of u. So that's u to the negative 1/2. And now my bounds, I can either keep them as x's. Let's convert them to u's here. So when x is 0, u is 4. When x is 2, 4 minus 4 squared is 0, u is 0. Note, I go big to small here. It's the way we want to leave it. This negative from the 1/2, you could switch the order by using that. I'm not going to bother with that, though. Okay, so this equals negative 1/2. 1 over square root u is u to the negative 1/2. So I do an antiderivative. I get u to the 1/2 over 1/2 from u is 0, sorry, not u is 0 to 2, but u is 4 to 0. Note the 1/2 sort of cancel here. And so what I get is negative 0 to the 1/2 minus 4 to the 1/2 here. So this gives me a 0 minus 2. So this whole thing works out to be 2. So we got a finite number. So not only does this converge, we know it converges to 2 here. So you got a finite number, and so that means that we get our integral does converge here. If, when you'd plugged in, probably the 4 here is at the 0 now that I marked it. So it's the 2 that was the problem, that's the 0. If this was like a 1 over 0, that could have given you something that goes to infinity and would be divergent. That didn't happen here. So this one converges. Next question. Same setup again. Determine whether this improper integral converges. Again, this is improper because if you plug in the 4, you get 4 minus 4, you get 0, and then you have 1 over 0. So I'm going to play the same game. I'm going to let u be 4 minus x here. Du then is negative dx. So I get an antiderivative, 1 over u. Then dx is du, but I pick up a negative. And then my bounds, I can convert them to u's. So when x is 0, u is 4. When x is 4, u is 0. Again, I could take this negative and switch the order. Let's actually do that here. So you get a positive integral 0 to 4, 1 over u du. Same thing here. Essentially here we're doing 1 over u's going from 0 to 4. Here we're doing 1 over the 4 minus x's, but we're sort of starting at 4 and going to 0. So it's sort of flip-flop the other way. Don't really need to know that, though. Okay, so what we get is antiderivative 1 over u, natural log absolute value u, from 0 to 4. So this is natural log 4 minus natural log 0, and those are positive zeros. So question here is, what is natural log 0? Well, if you look at a graph of y equals natural log x, what you get, so natural log 1 is 0, you get a graph that looks like this, sort of. And what's going to happen here is you get a vertical asymptote, and as x gets closer and closer to 0, but positive, the value of the natural log goes to negative infinity. So this is natural log 4 minus negative infinity. So essentially this goes to plus infinity. Doesn't really matter if it's plus or minus, but we're integrating something that's always positive here, at least if x is between 0 and 4, so it better be positive. So we get an infinite value. That means that our integral diverges. Next question. Here, not looking for convergence, divergence, kind of threw this in. We're doing an antiderivative of x plus 5 over x plus 1 squared dx. Okay, this one, there's a couple ways to do this. The way it's set up makes me think partial fractions. So we're going to do that here. What I'm going to do is I'm going to rewrite x plus 5 over x plus 1 squared. I'm going to rewrite this as a over x plus 1 plus b over x plus 1 squared. Then I'm going to multiply both sides by x plus 1 squared. The x plus 1 squared will cancel in this first one. Second one, x plus 1 squared over x plus 1 will give me an a times x plus 1. X plus 1 squared will cancel in the b over x plus 1 squared term. So I get this equation. I'm trying to find a and b. To do that, I'm going to plug in x equals -1. It gives me -1 plus 5 is 4. Point of -1 is then I get -1 plus 1 is 0. This term drops out. I get 4 equals b. So generally, I'm trying to pick things that make sort of things multiplied by a or b or c or whatever be 0. -1 is the one that works. I ran out of those here. So I'm going to try something simple. How about x equals 0? On the left, I get 5. Get 0 plus 1 is a. Get 5 equals a plus b. But I already know 4 equals b. So that's a plus 4. 5 equals a plus 4. That gives me a equals 1. So what I get here is x plus 5 over x plus 1 squared. And again, no calculus really here. This is just algebra. This is the same thing as 1 over x plus 1 plus 4, b is 4, over x plus 1 squared. So we just rewrote this rational function inside. And so now I'm going to do an integral. I can get an integral of 1 over x plus 1 dx plus an integral of 4 over x plus 1 squared dx. Now the whole thing here is this is easier to integrate here, each of these individually than the initial one. That's the idea anyway. Antiderivative 1 over x plus 1 is natural log absolute value x plus 1 plus 4 x plus 1 over x plus 1 squared is x plus 1 to the -2. So I get x plus 1 to the -1 over -1 plus c. So I get natural log x plus 1. Let's see, this will be a minus 4 over x plus 1 plus c. Okay, so that's our partial fraction approach. Not so bad here. Let's do this again, though. So we had an integral. It was x plus 5 over x plus 1 squared dx. Just make sure I wrote that down right. Yep. And let's do this one in green. We're going to do a different approach altogether. I can do a somewhat clever u-substitution here. By clever, I mean it's a trick I've seen enough times that I sort of know to look for it. What I'm going to do is I see this x plus 1 squared on the bottom. I'm going to let that u be x plus 1. Note here then x is going to be u minus 1. du is dx. So if I do that substitution, so again, this is a totally different way to do this problem. Hopefully I get the same answer. I get an antiderivative x plus 5, that's u minus 1 plus 5, over x plus 1 squared is u squared, and then dx is du. So I get an antiderivative of u plus 4 over u squared du, and then u over u squared, that gives me an antiderivative of 1 over u du, plus an antiderivative of 4 over u squared du. So what I get, antiderivative of 1 over u du is natural log absolute value u, plus 4, this is u to the -1 over -1, because 1 over u squared is u to the -2, plus c. So I get an absolute value, natural log absolute value u, it's absolute value x plus 1, not plus, I get a minus 4 over u, but u is x plus 1 plus c. So that's the same answer we got above. Here, this answer matches what we got here. So that's reassuring, I guess. So two different methods. Either do partial fractions or a certain u-sub that's kind of clever. I think the u-sub way works out a little bit nicer, but it's got to be balanced just right for this to work. If you had looked at something like x plus 5 over x plus 1 squared times x plus 2, then this u-sub probably isn't going to work out as nicely here. So there's just certain scenarios where those subs work out, u-substitutions work out. This happened to be one here. Probably the intent of this question was to have you do partial fractions, but if you can find slicker ways around these, more power to you. Okay. Here's another one. Now this one I'm looking at and thinking this is probably going to be partial fractions here. So what I'm going to do here when I do this, first of all, I have a degree 3 polynomial on top, degree 2 on the bottom. Degree of the top is bigger than, greater than, or equal to the degree of the bottom. So I'm going to start off doing long division. So I'm going to get x cubed, really plus 0x squared, minus 10x plus 10. I'm going to divide that by x squared plus x minus 12. Then x squared times x gives me x cubed. X times x squared is x cubed. X times x is x squared. X times negative 12 is negative 12x. And then I need to subtract this. X cubed minus x cubed is 0. 0x squared minus x squared is negative x squared. Negative 10x minus negative 12x is plus 2x plus 10. And then I'm going to get a minus 1. X squared times minus 1 gives me a minus x squared. Let's see, minus x plus 12. But I need to subtract that. So I'll get negative x squared plus x squared is 0. 2x plus an x minus negative 3x. 10 minus 12 is 2. So what I get from this is x cubed minus 10x. Well, let's just rewrite the integral here. What I get is inside the integral, I get an x minus 1 plus my remainder 3x minus 2 over x squared plus x minus 12 dx. So we simplified this to some degree. I can integrate x, I can integrate minus 1, those are no problem. 3x minus 2 over x squared plus x minus 12, I'm going to need to do partial fractions. So we're going to work on that fraction here. So I have 3x minus 2 over x squared plus x minus 12. First thing to do is factor that denominator. Turns out to be x plus 4 times x minus 3. And then the general form that we're looking for here is we're going to write this as a over one of the factors plus b over the other factor. You could switch your a and b around or switch the order of the x plus 4, x minus 3. It doesn't matter. You'll get the same answer in the end here. And then I'm going to multiply 3x minus 2 over x squared plus x minus 12. Well, really, 3x minus 2 times x plus 4 over x minus 3. I'm going to multiply both sides by x plus 4 times x minus 3. On the left, those cancel for 3x minus 2. On the right, the x plus 4 and the x plus 4 cancel. So I get a times x minus 3. B times x minus 3, the x minus 3's cancel. So I'll get b times x plus 4. And then I could expand this out, equate coefficients of x, equate the constant terms. I find it easier, or at least more satisfying, to just plug in values of x. So I'm going to pick x equals 3. I'm doing that because then 3 minus 3 is 0 and the a term drops out. On the right, 3 times 3 is 9, minus 2 is 7. Again, the a term is 0, drops out. And then I get equals b, 3 plus 4 is 7. B times 7, that gives me b equals 1. Then to make x plus 4 0, I plug in x equals negative 4. 3 times negative 4 is negative 12. I get negative 14. Negative 4 minus 3 is negative 7. So I get minus 7a. And then the b term is 0. Divide both sides by negative 7. And you get a equals 2. So what I get here, well, that's my initial integral of x cubed minus 10x plus 10 over x squared plus x minus 12 dx. By doing some algebra, we can split this into an integral of x minus 1, and then plus a over x plus 4, so plus 2 over x plus 4, and then plus 1 over x minus 3. So we get that. And now we can sort of do 4 separate integrals here. So again, just algebra, now do our calculus. Antiderivative of x is x squared over 2. Antiderivative of 1 is minus x. This is going to give me 2 over x plus 4 is going to give me a 2 natural log absolute value x plus 4. Technically, I'm doing a u-substitution, u equals x plus 4. And then same thing with this last one. I'm going to let u equal x minus 3. But if you follow that through, I get a natural log absolute value x minus 3 plus c. So that's really our antiderivative. This kind of ugly looking thing, but you can factor the bottom and do a partial fraction approach. Last question. Here we're estimating an integral. We want to know how many intervals do we need to guarantee an error of less than 0.01. Okay, so trapezoid rule. What we had here is our trapezoid rule is the error from the trapezoid rule. This is bounded above by, we had a capital M, which is some bound on a derivative. times b minus a to the third over 12n squared. Here. And the goal here is we want our error to be less than 0.01. By making n sufficiently big, we can drive this down, which will drive the error down. So what we're going to do is we want this term here to be less than 0.01. So now we're going to pick, or so we can plug in m and b minus a. Those are constants defined by the problem. So b and a are 5 and 0. So I can kind of ignore this error from the trapezoid here. So I'm going to get b minus a is 5 minus 0 cubed over 12n squared. So less than 0.01. M here is supposed to be an upper bound for the second derivative. For the trapezoid rule, it's second derivative. So f of x equals x to the fifth plus 4x to the fourth, whoops, minus 2x cubed plus 5. F prime of x then is 5x to the fourth plus 16x cubed minus, let's see, 6x squared. And then the second derivative is 20x cubed plus 48x squared minus 12x. So I need to figure out, for x between 0 and 5, where is this minimum here? So normally I would just plug in the right endpoint, but that would be if I had a plus there. So I have a minus 12x, so that worries me that maybe my graph has a maximum, some kind of local maximum between 0 and 5 here. So what I'm going to have to do is probably graph this. So I'm going to pull up a calculator here. Let's go back to default state. Whoops, show hide, get rid of everything. Okay, so I'm going to graph this 20x cubed plus 48x squared minus 12x. So I'm going to do y equals 20x to the third plus 48x squared minus 12x. And my window, really I only care about x between 0 and 5. I'm going to graph this. I'm going to suppose, yeah, it just goes up somewhere huge here. So I don't really know what happened here. Let's see if we can find a, well, let's see. We want to get 0 to 5. We want to do is y range. So let's do our y max instead of 10. Let's make this 100. Do our graph. Still not big enough. Window, let's make that 1,000. There probably are more efficient ways to go about this, but I guess that's what I'm doing here. Make that 1,000. Still not there yet. We go to 10,000. So now I'm thinking that this may have been a mistake doing things this way, but there I go. So it looks like this is increasing all the way. I could have taken a third derivative here and shown the third derivative is always positive. I'm guessing was going to work out just fine here. It's probably the way to go. Or the third derivative, once I get above a certain value, is always going to be positive. Means this is the second derivative is increasing here. You could use some of your Calc 1 skills. But it turns out, by graph, this is maximized for x equal to 5. So m is going to be second derivative evaluated at 5 here, and that's going to be, let's quit out here. I can do variables, y1, which was our second derivative, plug in 5, gives me 3640. So you plug in 5 for x, you get 3640. So I get a 3640 here. Okay. Now I just need to solve for n. So I'm going to move n squared to the other side. I get 3640 times 5 minus 0 is 5. That's 5 cubed over 12. Less than, I multiply both sides by n squared and divide by 0.01. Now dividing by 0.01 is the same thing as multiplying by 100 here. And so what I'm going to get is my n is greater, sort of switching the order, than square root. I get 3640, 5 cubed is 125, divided by 12, and then the 0.01 can go to the top as a 100 here. So I'm going to get that square root. So I get a square root 3640 times 125 times 100 and divided by 12 here. Hit enter, and that's 1947. And so this has got to be greater than 1947.2, 47.2, and n has to be a whole number, so the n we want is 1948. So we're going to have to do 1,948 intervals. Sounds like an awful lot to do by hand, but if you're going to use a computer to do this, that's not so bad. A computer is probably going to go through 2,000 intervals if you're just doing this once here in pretty short order here. So that's feasible to do. Okay. And we're going to get error less than 0.01. Now we're going to use Simpson's rule. Simpson's rule, a little different. Error bound is very much like this error bound for the trapezoidal rule. So the error for Simpson's rule that we're using is this error is an m. Note this is a different m. For Simpson's rule, we use an upper bound on the fourth derivative. And we get b minus a, not to the third, but to the fifth, over 180 n to the fourth. So the power of Simpson's rules, instead of an n squared, I get an n to the fourth. Instead of a square root, I get a fourth root. Now I'll get a bigger number in here, but I take a sort of higher root, can give me a smaller number here. And I want that less than 0.01. Okay, so we're going to fill things in. M, I need again a fourth derivative. So I knew f double prime of x was 20x cubed plus 48x squared minus 12x. So we take a third derivative, gives me a 60x squared plus 96x minus 12. And then our fourth derivative is 120x plus 96. Note, this is always where each of these terms is positive for x from 0 to 5, so I don't have to worry about where the local max is. So what I'm going to do is m is going to be the fourth derivative evaluated at 5. Note, this is going to be maxed out as 120 times 5 plus 96. 120 times 5 is 600 plus 96. So we're going to use a 696 for m. It worked out nicely. I didn't really need the calculator. So what I get is a 696 times, let's see, b minus a, that's 5 minus 0 to the fifth, over 180 times n to the fourth is less than 0.01. And so then I can move the n to the fourth to the other side. I get a 696 times 5 to the fifth over 180. And then I get a 0.01 in my denominator, less than n to the fourth. I'm going to just switch sides, and I get n is, not equal to, n is greater than, I'm going to do a fourth root by raising this to the 1/4. I get a 696 times 5 to the fifth. I'm not even going to think about what that is. That 0.01 on the bottom I can bring to the top as 100, or I could just leave it there since I'm going to use a calculator anyway. Get 180 to the 1/4. So moment of truth, can we beat the 1948? 696 times 5 to the fifth times 100 divided by 180 to the, instead of 1/4, I'm just going to use 0.25. Hit enter. And we get quite a bit smaller number here. So this is greater than 33.1 here. I mean, I don't really need a round. I need a whole number. So here I need n is 34. So Simpson's rule lets us get by with quite a bit smaller. This is certainly within the realm of doing this on a computer here, particularly if you're going to repeat this a bunch of times. 34 is what, like maybe a factor of 60 from 1948? Let's check that. 1948 divided by 34. Yeah, something like, 57. So something like a factor of 60, you're saving number of iterations. Turns out if you look at the way that you do Simpson's rule and the trapezoid rule, the difficulty is about the same for each of them here. Maybe Simpson's rule is ever so slightly harder, but it's essentially the same thing here. So this is probably Simpson's rule will be a much better rule to use if these error bounds we had were sort of close to accurate in the actual error. Again, this is an upper bound, so maybe you can get by less for one of these. Who knows? Okay, so this ends our review questions for exam 2.